Remember back to that first step in the proton-proton chain, where two protons fuse together into a heavy hydrogen, a positron, and that elusive neutrino. What is that thing? Well, for starters, what I'm going to say is that it's a weakly interacting particle. It has no charge and very little mass. We actually only got a definitive idea of how much mass this thing has within the last decade of the recording of this video. So, let's talk about some of the weird things associated with neutrinos now. For starters, here's a simulation of experiments going on at the Large Hadron Collider of particles coming in, flying together, and see what material gets output from those collisions. That's one way to make neutrinos. Others will be the solar neutrinos that's being constantly generated in that fusion chain in the sun. So get this. In the time it takes for you to read this sentence, about 400 trillion solar neutrinos will pass through you. You are being bombarded constantly by neutrinos. And you just don't care. Why not? Right? If there's trillions of particles flying through you right now, why do you not care? Because they don't interact with you. They just pass right through you. You could think of the sun being this Gatling gun of neutrinos, just constantly firing them off. Bam, 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 bam. But the bullets, these neutrinos, they just pass right through you. These things are so weakly interacting that they'll travel through space, through you, through the depths of the planet, and not really interact. They'll just keep on going. To really emphasize this point, to hammer it home, remember back that the photons, they take upwards to 100,000 years when that photon gets generated in the core and its random chaotic path out of the sun. 100,000 years for the energy from the photons to get out of the sun. But the neutrinos, seconds. They get produced in that first step, the proton-proton chain, and they'll travel near the speed of light and just jettison out of the sun in a matter of seconds. Now, here's a really powerful tool of these things. If we can count the neutrinos, how powerful they are in terms of their kinetic energy, where they're going, and count just the volume of them, the term we'd use is the flux of neutrinos. By counting that up, we understand the rate of fusion in the interior of the sun. Think back to earlier in this section, how we figured out how much energy the sun has based on its luminosity. We just said, well, how many photons? How powerful is it? In this sense here. And if we can correspond that to the amount of neutrinos leaving the sun, this gives us an amazing probe to understand the physics of what's happening deep in the interior of our sun. So one of the difficulties with neutrinos is that you just can't build a telescope for them. They'll pass right through the lens. They'll pass through literally the material that the telescope's made out of. So how do you actually how do you detect a neutrino? What you have to do is be very patient and, for a lot of cases, go deep underground. These are examples of experiments that went upwards of 2 kilometers underneath the surface of the planet. The reason you go deep underground is because you don't want stray particles interacting with your experiment. You want just the neutrinos. So you let Earth's surface, material above you, be a blocker to try and block off any stray noise entering your detector, because all you want is neutrinos. And what you'll do is you'll have this gigantic tank. This one here is about 12 meters in diameter. And you'll fill it with very pure, clean water, or in this experiment here, you'll actually use what's called heavy water. Remember back to that deuterium stuff that we talked about? That hydrogen with an excess neutron on it? Well, heavy water is H2O, but the H's have excess neutrons on them. Regardless of the explicit trick that you're going to use, basically what you're waiting for is a cascade of neutrinos to pass through this, go through your detector, and eventually, if you're patient, one will interact with the water, and that'll generate a photon for your detector to pick up on. Here's an example of the sheer size of a neutrino detector. This is two guys on a little rowboat sitting on a sea of water, and they're literally swimming around installing these detectors here. These are photon detectors. So what's happening is that let's get the right color, as a neutrino will pass through this thing, some of it will eventually interact with the water. It's not that it never interacts with matter, it's that it has a low probability of interacting. So let's say you have your neutrino and it's passing through the water inside this gigantic detector. Photons can try and travel through. You'll have your photon trying to move through this. So remember that the speed of light, while is 3 times 10 to the 8th meters per second in vacuum, inside water it slows down. Think back to section 5 when we talked about these things, and section 6 when we talked about optics. What's happening is that the speed of light will be reduced when it's traveling through water. Think about your top speed when you're running on the ground versus how quickly you can swim. All right? This neutrino, when it does eventually interact with the water, it has the potential to be moving faster than the speed of light in that water. This is analogous to a sonic boom. A photon is traveling at some reduced rate, and the neutrino, when it does interact with the water, will be moving faster than photons in the water. And that creates this big kaboom, just like a sonic boom, but for photons, an optical boom. And that optical boom will get picked up by all of these detectors going, oh, an event happened. Holy crap, we just measured a neutrino. Remember that I said that one thing we want to use is the number of neutrinos to understand the fusion going on in the sun. So we could build this in our scientific model idea and say, hey, hypothesis. The energy coming from the sun is related to the number of neutrinos it creates. So count them up. That's our test. Count the number of neutrinos that the sun's producing. And this became a huge problem for us. We only recently solved. When we did the experiment, we only got a third of the number of neutrinos that we thought we should measure. We know how powerful the sun is by just looking at the luminosity of the sun, see how much power is being radiated from it every day. And that should cross-reference with the number of neutrinos. But we first built our neutrino detectors, and we were getting a third of what we had expected. So this only leaves us with two possibilities. Either we didn't understand fusion, or we didn't understand neutrinos. We can really try and argue for ourselves that we understand fusion. We understand enough to make bombs or power plants now. So we think we understand the physics behind fusion processes, which leads us to the possibility of maybe we don't have the full picture on neutrinos. This is what became known as the solar neutrino problem. We were getting a third of the number of neutrinos that we had expected based on the luminosity of the sun. So this solar neutrino problem was this issue of only measuring a third of the number of neutrinos that we expected to get from the sun. And the resolution turned out to be that there are 3 flavors of neutrinos. There are specifically 3 types of neutrinos. And they'll oscillate. You'll have your what's called an electron neutrino, and it can over time shift into a muon neutrino or into a tau neutrino, and back and forth in this weird kind of triangular scheme. And to try and understand this, how can a particle just morph into another, or back, or into a third? We're going to use this idea of coupled oscillators. And this is how the motion of one oscillating object can convert into another. So let's get a model of what I mean by coupled oscillators. I'll have 2 pendulums, and they're right now independent of each other. I can have one going that direction, another going that way. I'm going to shift my head out of perspective. And the motion of these two oscillators are independent of each other. It doesn't really matter what one does. Now, let's couple them. We're going to stop. And my coupling is going to be a nice little spring. So by coupling them, all of a sudden, the motion of one has an impact on the motion of the other. So I'll start one at rest, I will stretch the other one away, and we'll see the motion that unfolds. Let me get out of the way. Notice how the motion shifts. Which one's the moving object? We'll keep transferring from one pendulum to the other. Here, we'll restart it. Bring it to a stop. I'll let this one be stretched out. So, which one's moving keeps bouncing back and forth, transitioning between the two oscillators. And this is what we mean by coupled oscillators. The motion of one has an influence on the other. And in this very simple example, we can see how you can go from one moving to transferring the other and back. So with this idea of the coupled oscillations, we're able to resolve the solar neutrino problem. Look at this way. What's the probability of finding a neutrino in a electron state, muon state, or tau state? The probability of that neutrino when we measure it being one of the states is basically dependent on how far that neutrino has traveled and its energy. Here it is, first produced in the core of the sun. And so it's oscillating as it propagates. You can think of it going back to that simple picture we had, that video we played, of it's the left pendulum oscillating, then the energy transfers, and now it's the right pendulum oscillating. So it's in some other state. And then keep going, that energy transfers back into the left pendulum, and it's the left one that's predominantly moving. And this is what I mean by the coupled oscillations. The neutrino will oscillate between very likely being in this electron state to this muon or tau state, and then back. So with that resolve, we finally learn new physics, we understand the three types of neutrinos that exist, and we can find all the solar neutrinos from the sun. Remember, when we first built these, we only knew of one type of neutrino, and so we were only detecting a third of what was out there. One of the underlying goals of counting neutrinos was to understand what's going on in the core of the sun, and we have other tricks for this too. This is an absolutely cool trick called helioseismology, and basically the sun's surface itself is a gigantic speaker system. Here's how it works. A segment of the sun will be falling in, moving inwards. That'll be redshifted. While another section will be blue shifted. It's being pushed up, driving outwards. So the surface layers of the sun literally act like a giant speaker. Speakers pulls in, pushes out, pulls in, pushes out. And so there are sound waves rippling throughout the entire surface of the sun. By measuring the speed of these waves, we get an idea of what the composition and the depth of material in this layer of the sun. We're literally probing the geology, if there were rocks. We're probing what the interior of the sun looks like based on just sound waves propagating through the material. Now this stuff is so crazy that people have downloaded it and turned the sun's sound waves into frequencies that our brains can interpret and understand. So the highlighted text here is a link. I highly recommend everyone click on these and just play around with the different modes of sound that our sun produces.